Um, right. So polar coordinates gave us a alternative way, a different map, if you will, of describing points on the plane. So instead of describing points on the plane using using Cartesian XY coordinates, we use a pair r and theta to describe the distance from the origin, or this is called the pole, and this is using your r and the angle with a positive x-axis, right? So and the positive and theta with the positive x-axis. This is the theta. Okay. The convention we take is r is always going to be non-negative when you're actually giving points on the plane, and theta usually when you're describing a range, a region in your plane, theta can be in any 2 pi interval. All right, conventionally, usually it's taken minus pi to pi or 0 to 2 pi. As long as you get 360 degrees of rotation or 2 pi radians of rotation, then you're good. Let's do a quick warm up, perhaps. So let's consider the following region. So this is your XY plane. And I'm going to draw, well, 2 rays, which are part of lines. So let's call, this is a line y is equal to x. This is a line y is equal to minus x. And I'm going to shade in the following region down here. So what is the shaded region in polar coordinates? So this is my shaded region, omega. So maybe the more straightforward one here is, let's say r is always non-negative still, but what are my bounds for theta in this case? So what's the lower bound for omega here? Right, so certainly you could do, we have this angle here, which is the lower ray of y is equal to x, right? This makes an angle of just of 180 degrees plus 45 degrees with a positive x-axis, or in other words, pi plus pi over 4, so that would be 5 pi over 4. And then you look at the angle again, so this is 180 plus 90 plus 45 again, so that's 7 pi over 4. Or in other words, you also just subtract 45 degrees from 360, and in radians that's 7 pi over 4. Or equally valid is also Mitsuka's answer, which is r is greater than or equal to 0, and theta excuse me, is going to be, if you instead describe theta, instead of going from 0 to 360 degrees, or 0 to 2 pi, you could also describe it as minus pi to pi, or minus 180 degrees to positive 180 degrees. And in that sort of choice, you could also describe this angle here as making minus 3 pi over 4 radians with a positive x-axis, and this angle here being minus pi over 4, minus 45 degrees with a positive x-axis. So you could equally well describe this region as minus 3 pi over 4 to minus pi over 4. And actually, you could also continue on. You could choose any sort of 2 pi within any 2 pi interval. Let's say from 2 pi to 4 pi. You could also decide to count your angle that way, and that gives you a valid region for theta as well. But these are the 2 most common ways of describing this region. All right. What's important to know is you want to be careful not to mix up these 2, right? It would not be valid to say theta between minus 3 pi over 4 and 5 pi over 4, for example, right? If you go from minus 3 pi over 4 to 5 pi over 4, then you've gone a full 360 degrees, and that's definitely not what this region is. So we just want to make sure that you don't mix up the bounds here. Okay, so that's a quick refresher, hopefully, on what this is. At the end of last class, we looked at one example of a cardioid, right? This was a polar curve, roughly heart-shaped. And what I pointed out was, and in a lot of these polar curves, they're very hard to sketch, but at certain angles, you have a rough idea of what the point your curve has to go through, right? Because if you have an expression of r is equal to 1 plus sine theta, then for theta equals 0 degrees, 90 degrees, 180, 45 degrees, and so forth, some values of sine theta for that. And if it's something particularly simple, then you're able to at least know for sure which points are and are not on your curve for at least certain angles, right? And that gives you a rough idea of what curves, if I show you 4 curves and then give you one single polar equation, you should at least be able to say which curves are plausible, which diagrams are plausible for a given equation and which ones are impossible, just by looking at which points they contain. So let's take another example here. And here it's just sketch the polar curve given by r is equal to 1 plus 3 cosine phi. All right, so one way you could do this is, well, try out a lot of points like we did last time, right? For a given theta, plug it in and see what r comes out as, and try to put in a few points and join them up. But here's another alternate way of doing it, which is a little bit more precise. And the first thing is to plot this curve on the r and theta axes. All right, so what I'm going to do here is write r here and theta here. Maybe I'll make the scaling a bit better. And so r, let's say I have 2, 4, say minus 2 here. So and let's do maybe pi over 2, pi, and 3 pi over 2, and 2 pi. All right, so what we could do here is look at what this curve is telling us, which is we could it's pretty straightforward. If you think back to maybe high school pre-calc, what this curve is, right? We definitely know what r is equal to cosine theta is, right? That's just a cosine curve that looks like in this scaling, it looks like this, right? Just a wave, and at 0 it's equal to 1. So we're going to scale that by 3 times cosine theta. So 3 cos theta is going to be that same wavy curve, but its magnitude is going to be 3, right? Its amplitude is going to be 3 instead of 1. So it'll look something like this. And then the plus 1 here just translates everything up 1. So instead of the peak happening at 3, it's going to be happening at 4. And the trough is going to happen at minus 2 instead of minus 3, because if you translate it up everything by 1. And so what we get is the curve on the r and theta, coordinates. R is equal to 1 plus 3 cos theta looks something like this. There's our curve. R is equal to 1 plus 3 cosine theta. And now using what this curve looks like, this tells us how your radius varies at angle theta, right? So if you translate this back to the xy plane, so here's my xy plane. What this is telling me is at angle is equal to 0, my radius is going to be equal to 4. So I'm 4 away. At angle 0, right? Remember, that's on the positive x-axis itself. I'm going to be a distance 4 away. Let me put in some tick marks here. So that's 2 and 4, 2, 4. So what's happening is at angle 0, I have my radial arm pointing over here at 4, right? So there's a radial arm that points at 4 here at angle 0. And then as I decrease my angle to pi over 2, as I decrease my, if I increase my angle from 0 to pi over 2, my radial arm is going to diminish in length, right? It's going to shrink from 4 away from the origin, all the way to 2, a distance of 1 away from the origin, right? At 1, this is going to be equal to, or at pi over 2 rather, at theta equals pi over 2, cosine of pi over 2 is 0, right? So r is going to be equal to 1. And so I've shrunk all the way down to 1 at that point. All right, so I've traced out the curve such that at pi over 2, I am definitely at 1 away from the origin. And it's my curve traces down, something that's constantly radius 4 looks like this, but my radius isn't constant, it's shrinking from 4 to 1. So it looks maybe something like this, right? You can imagine a path going like this that shrinks constantly to radius 1. And then something weird happens here. Here I have theta goes to pi, right? At angle pi. So as I go from theta is pi over 2 to pi. Just looking at this equation here, r actually goes negative, right? But previously I said conventionally, we're always going to take r to be positive. But the one case where it's useful to actually allow negative r values is when you're trying to plot these curves. It's when you're trying to imagine what these curves look like. All right, so what this is saying is at an angle of pi, right, which is along the minus x axis, so it's a ray pointing to the left here. At this angle, I'm a distance of -2 away from the origin. So if this were +2, then I'd be simply here again, right? I'd be 2 away from the origin in the direction minus pi. Or sorry, in the direction pi, right? Now instead, according to this relation here, my polar curve, r is actually -2 at angle pi, which means that instead of looking at the positive x-axis and taking 2 away in that direction, I'm going to take a distance, I'm going to take -2 in this direction, which is actually going to be +2 in the opposite direction here. So what's happening is at pi, I'm here. So at this point here, this is that r is equal to -2, theta is equal to pi. So the one case, let me reiterate, you should always, when you're plotting points on their own and describing regions, you should always make it such that r is non-negative. The one exception to this rule is when you're given a polar curve. Then you have to interpret it such that r does take on negative values. And when they do, that just means instead of taking the usual positive direction and the direction of the angle that you're given, you want to take the opposite, all right, the opposite direction of the ray that you're given. So that's why r -2 and theta equals pi happens here. So what's happening now, if I look at this curve here, I'm starting at 4, at angle 0. So at the purple curve here, I'm starting up here. And then I keep on going until I hit an angle of pi over 2. And at pi over 2, I'm going to end up over here. And then at some point here, I'm going to cross 0, right? In the r and theta in the r and theta diagram here. Whatever theta that is when r is equal to 0, at that particular theta, I'm going to be at the origin. And then for this entire region here, my r is going to be negative. So as theta keeps increasing up until pi here, I'm actually going to sweep out in this direction here again. So what's happening here is I have a curve that looks like, so that corresponds to this portion here. Then I have a region that looks like, shoot, I'm out of colors. From this portion here, I'm actually going to go down to 0 here. And then there's going to be a portion here which sweeps out this region here. All right, or at least somehow it looks roughly like that. And then if you now go back along this curve, it's going to be sort of the reverse image of this. So you're once again going to look at something as you go from pi to 3 pi over 2. So this angle here up until this angle here, you're going to start with negative r here, continuing until you hit 0 again. And then you're going to get positive again here, and you're going to sweep something out here. All right, so the rest of this curve just looks like something like this. All right, so this is a slightly different way of approaching these types of problems to try and picture what curves are admissible or not. You could think of this diagram here as a continuous version of what we had last time, right? Last time we had discrete values of theta that we plugged in, and then we looked at what r is going out. But for very nice algebraic expressions in theta and r like this, we could use we could graph this in our heads and see precisely what the curve traces out. This gives us a continuous version of what we had last time, and it could help with our intuition for what's going on in the actual polar curve situation here. Let's go on to maybe converting some of these algebraic curves in r and theta coordinates back into xy coordinates. All right, so sometimes it's also useful. So maybe you recall we had conversions from xy, well, I guess between xy coordinates and r and theta coordinates. And roughly the conversions look like this, right? You could have, if you're given something at r and theta, then you had x is equal to r cosine theta, y is equal to r sine theta. And these were applications of high school trig in essence. And to go the other way was a bit complicated, but you had the relations r squared is equal to x squared plus y squared, so you just take the square root. And then you had tangent of theta had to be equal to y over x, right? And for this portion here, you usually take theta as equal to arctan of y over x. And depending on the settings of your calculator or whatever, that usually gets you a single value of theta, but tangent has a period of pi or something, right? So you actually get infinitely many solutions of theta here. So you got to pick and choose your theta as you so please, for the theta to land within your allocated 2 pi interval for your angle. Okay, so let me address some questions in the chat here. So can I re-explain why negative r is on the positive x side? Yes. So let's say r and theta. So let's say, let's look at the precise point where r goes negative. All right. So at this turquoise color here, this is theta. This is the angle theta star. Theta star is going to be equal to in these coordinates. I want when r is equal to 0. That means when 1 plus 3 cos theta is equal to 0. All right, so this means that theta star satisfies cosine. Theta star is equal to 1/3. 1/3. Right. I don't really care. You could solve this on your calculator, find precisely which theta star it is, but for our purposes, let's not care too much about this. So what this is saying is at this angle here, this is the angle theta star, all right? When I say theta star, I just mean, this angle with a positive x-axis is theta star. And, I'm going along this curve here until I hit theta star, everything is nice, right? We all know, hopefully from last week and our discussion here, we're pretty comfortable with what it means for r to be positive when theta is positive, right? For every single angle here, before things get a bit messed up, your theta's, going on and r is always positive or at least non-negative. Finally, your r disappears, right? At this critical angle theta star, you've come back to this origin and you've hit this orange point here, right here. Now, from every angle here until, by the way, because of the symmetries, precisely when this crosses 0 again. This is actually going to be, well, actually, I shouldn't say too soon. This should be 2 pi minus theta star, right? I think that's how it works, right? So this then gets you precisely what the crossing here is. So this is kind of symmetric, all right? So wherever this crosses 0, there's going to be another ray here where this crosses 0 again. So let's just focus first on this portion here and then this until pi, all right? So from this angle here until this angle at pi, your r is negative. It's going from here to here and it's all negative. So now draw for every single possible ray here. So this is some theta that's in between theta star and pi. Let's say that's this angle here, all right, between theta star and pi. Now you read off this is a negative, this is negative r. R is like something between -1 and -2, for example. Then instead of going 1 or 2, instead of, let's say it's at 1, it's at -1. Then instead of going 1 away in this direction, you actually want to extend this ray out in this direction here. And then what you're going to do is instead of taking, let's say at this angle theta, which is here, you're at -1. All right. So instead of going 1 away in this angle theta, you want to look at, extending this backwards and take 1 away in this direction. And that's going to get you on this portion of this curve. All right. This portion of the curve here. So as soon as you go negative, you're sort of like in reverso world, right? You put a mirror here, you extend the line backwards, you extend whatever ray it is backwards, and then you go the distance along that line that corresponds to your minus direction. All right. So take the magnitude of how negative you are, extend your ray backwards, your point is going to be that distance in the backwards ray. So that's why this loop is now going backwards for these angles. From every angle here all the way to until you're positive again, these are all, in a sense, reflected. You put a mirror here and you sort of reflect your situation. And every single point here corresponds to the negative of the angle. Right, so we had these conversions last time. I won't draw the picture, but hopefully you have the notes so you can remember how we got this basically from trig, and this is also from trig. All right, so everything is just trig here. And now there's, last time we did an example where I gave you single points in xy and single points in r theta and had you convert them. And I noted that in a lot of cases, you could actually just eyeball them, and instead of going through, especially using this this conversion here, you really just, given any single point in xy, you could roughly, if you know what's going on and if the points are very nice, then you could just read off how far it is from the how far it is from the origin, and then find an angle that corresponds to it just using, I guess, just using geometry. All right, so in a lot of cases, if the points are very nice and and the questions are contrived like they are in classes, then you rarely use this. The one situation that these conversions do use, are useful, are when you want to express polar curves and Cartesian coordinates and vice versa. All right, so for example, you can use these to convert polar curves to Cartesian and vice versa. Let's do an example. Let's do two examples actually. Let's do example A, which is r is equal to 5 cosine theta, and then B is going to be r squared. Oh well, I didn't even finish this. Hold on. This is awkward. Let me try and find this problem. I didn't finish this. There we go. Okay, that's correct. There we go. R squared cos 2 theta is equal to 1. Okay, so these are the two curves that I have in polar coordinates. Maybe I'll give you 1 minute just to think about these and see if you could tell me what curves these are in Cartesian, in the sense that, could you tell me, is this a line? Is this a parabola? Is this a circle, etc.? Is this a line, a parabola? Is it a circle? So here's a strategy, right? So one way we could do this is plot it, but you don't have a calculator. So how are you going to plot it? The other thing you could do is try and do a setup like this, but this takes a long time, right? So here's another way, which is to convert. Now, to convert these things, you have an expression in r and theta, and you want to convert in xy. So the dictionary you want to use is on this side, right? You have something in r and theta, so you want to do the substitution so that x is equal to r cos theta, y is equal to r sine theta. So try and figure things out. Or actually, well, dictionary actually goes both ways. You have all these relations here, and depending on the scenario, I guess really is the version you want to use. You basically want to make this make this setup only involve x's and y's. So one way you could do this is try and make your life easier and multiply both sides by r. That gets you r squared is equal to 5 r cos theta if you multiply by both sides. And what's the point of this? Well, it's a little bit of trickery, right? Because as soon as you multiply r on both sides, r squared is very nice in terms of your conversion. R squared is just x squared plus y squared. And similarly, r cos theta is very nice. R cos theta just gets you an x, right? So now you could do your substitutions, which means on the left-hand side, you could substitute r squared with x squared plus y squared. And on the right-hand side, you have 5 times r cos theta, which is x, right? So altogether, we could bring everything to one side, x squared minus 5x plus y squared is equal to 0. Now, this still doesn't look quite like a circle, right? There's some work to be done. What you could do is complete the square. Well, what you should do, I should say, that there's really only one way to proceed. So you could complete the square, and what's that going to get you? Well, this is going to be x minus, oh shoot. Right, so this is going to be x minus, how the heck do you complete this square? So there's 5 over 2 times, or just 5 over 2, right? Is that right? Yeah, okay. So let's see what I did here. If you do a square of this, right, this is going to be x squared minus 5 over 2x, right? Minus 5 over 2x again. So that together should get you minus 5x. And then there's an extra bit, which is plus 5/2 all squared. So you don't want that because there is no plus 5/2 all squared here. So you subtract that off again. So this is minus 5/2 all squared. And then your y stays the same, and that's 0. What I've done here is, once again, I've substituted this portion here with this, and y squared stays the same, and that's what you get. And then what do you get? Well, you could clean everything up, and this is x minus 5/2 squared plus y squared is equal to 5/2 squared. So this is a circle centered at 5/2, right? So that's 2.5, right? So Gabriel's right. It's 5/2, and 0. Radius is 5/2. All right. So in this case, well, in a lot of cases actually. So if you're not actually asked to plot out the polar curve, for very simple contrived cases, you could do these substitutions, and sometimes the substitutions get you a very nice algebraic equation of the type that you recognize as a line or a circle, and this is how you do the substitution. Let's try B here. All right, so r squared cos 2 theta is equal to 1. And so does anyone know of a good what cos 2 theta is? Okay, Raphael says hyperbola. That does turn out to be correct, but let's try and derive that ourselves. So what identity is nice for cos 2 theta? Right. So okay, a lot of ones here. Let's do this example. I'll show you the one I choose here, and then I'll actually tell you how to get most of the ones you need for this course. All right, as a digression. So let's use the identity. So trig identity is r squared times cos squared theta minus sine squared theta. So that's your expansion for cos 2 theta. All right, it's cos squared theta minus sine squared theta equals 1. All right, so now multiply out by, this is r squared cos squared theta minus r squared sine squared theta. So that's r cos all squared minus r sine all squared. So that's going to be, well, r cos is x, right? So that's x squared minus y squared is equal to 1. And this is a hyperbola. What's a hyperbola? Let me draw it out for you. So let's look at the set of equations, or the set of points that satisfy x squared minus y squared equals 1. So at y equals 0, so this is your x-intercept. This tells you x squared is equal to 1. So x could be plus or minus 1, right? So you have intersections at plus 1 and minus 1. And you know that you could actually never get, you definitely have no y-intercepts, right? To have a y-intercept, you'd be x equals 0 and minus y squared equals plus 1. That's just not possible in the reals, right? So in essence, this is going to end up being this is a complete digression, but you could also do this as x plus y, x minus y is equal to 1. That's just how you factor x squared minus y squared. And so you see there are two asymptotes here. The line y is equal to x, and the line y is equal to minus x, which I'm trying to draw here dotted, right? Those correspond to, this is going to be y is equal, at y is equal to x, this term is 0. At y is equal to minus x, this term is 0. And whenever one of these is 0, you cannot be on this line, right? Because as soon as one of these vanishes, the product is no longer 1. So you can never be on any of these lines. And the best you can is just approach these asymptotically. What you end up doing is you have a hyperbola that looks like this, right? So this is your hyperbola, and in these directions they go off, and they just get very, very close to this slanted line here, but never touches, and the same thing in this direction. So that's what a hyperbola is. Let me do a couple of notes, because I know you're all panicking. Is this on test? Do I need to know this, etc.? So you won't need to know hyperbolas in detail for this. All right. So in 10.5, which we're not really going to cover in the text, where it tells you, where the vertexes of parabolas, hyperbolas, where, they have all these names for the conic sections. All right. They're called conic sections between if you have a hyperbola or a parabola or a circle. These are all essentially, if you take a cone, that's just a V shape. And you sort of slice it differently by planes. If you slice it horizontally, you get cross sections of circles. If you slice it vertically, you get hyperbolas that look like this. If you slice at a particular angle, somewhat askew vertically, you get a parabola. These are all conic sections. These are, why mathematicians originally came up with these geometric shapes. We're not going to bother with too many of those. You just need to know roughly what these look like, all right? So when you have something that's x squared minus y squared equals some constant c here, that's positive, then you know it's a hyperbola. You should know visually that it's some hyperbola opening up this way with perhaps a different intersection here. If it's y squared minus x squared equals some constant here, it's a hyperbola opening the other way, up and down. And that's all you need to know about hyperbolas, all right? Things that look like x squared minus y squared equals a constant, or maybe x squared over rescaled this and that. You could just stretch this in various ways and just know roughly, what this is. Just know this is not a circle, right? And that's all you need to know for hyperbolas. In this particular case, this is a hyperbola. So note for this class, just know the general shapes of hyperbolas. Let's say things of the form, x minus, x over a minus y over b squared is equal to c, 2c squared, or and the other direction. All right, so these are just all you're responsible for. You don't really need to know any specifics. And it's easy enough with these just to find out where the intercepts are, and that's all you need to know. The other note is the trig identities to memorize. You should know these off the top of your head. So, once again, you could, now that I've written it down on these notes, you got to refer to this on your tests, but your exam is definitely closed book. So you'll have to memorize some. Fortunately, not too many. The first one is sine squared theta plus cos squared theta is equal to 1. Second one is sine 2 theta is equal to 2 sine theta cos theta. And the third one is, it would really suck if I made a mistake here. So someone please yell out if I make a stupid error. But this is, okay, so cosine 2 theta, like we just used, is cosine squared theta minus sine squared theta. And then there are other ones that you probably see more often. They're the half angle identities. But I'm telling you, you just need these three to derive all the rest, because you get a couple options with this one, A and B versions of this. You could basically, rewrite this in a form you want. If I do cos squared theta and substitute in, if I keep this here and I substitute in sine squared theta using 1, then I get cos 2 theta is equal to cos 2 cos squared theta minus 1, just by subbing in 1 and eliminating sine squared. And I could do it the other way, and I get cosine 2 theta is equal to, let's see what I do. Oh, right, 1 minus 2 sine squared theta. And then you divide out as necessary, and you get some other fancy identity. So these are the three, these are the three that you need to memorize, and the rest fall out from there that you need. All right, so let's move on to, by the way, this roughly concludes what we need for chapter 10. I know in the course, we've skipped almost entirely 10.4 and 10.5. 10.5 are more conics and hyperbolas, but this is all we need. 10.4 has to do with velocities and tangents, which we'll do in a lot, in much more generality later on. So we may revisit some of this material in 10.4, but it's not crucial. It's not, it's not going to be covered too much. So, well, it's not going to be covered at all because we haven't covered it. But you'll see the concepts later on with different coordinate systems, and we'll need to know that when we cover it. So for now, this is the end of the chapter 10 section. And let's move on to the chapter 12 unit. So these are going to be three-dimensional coordinate systems. All right, so Cartesian coordinates in R3. So now we're looking at physical space in 3 dimensions. We're no longer confined to the XY plane anymore, and this more immediately models our real world, right? At least for classical physics, right? Three spatial dimensions, and we would like to describe objects in them, how objects move, functions that take as input 3 variables, because they model things like potentials in physics, and more generally, you can have functions of several variables. So let's familiarize ourselves with how this all works out. So here we are. You have the XY plane, but now you're also having a vertical direction Z. a point P in R3. So I'm sometimes going to refer, to use some set notation here. So this just means a point inside R3 can be described by coordinates X, Y, and Z. All right, so here's P, and it has coordinates X, Y, and Z. And X, Y, and Z, as you might have guessed, it's based on how high up you are. This gets you the Z. And then if you imagine casting a shadow vertically downwards, so let's say the sun is high noon, it's shining downwards, then you also have a X and Y coordinates on the shadow. The shadow lives in the XY plane, and you can read off of the X and Y coordinates there. So altogether, you could specify a point in 3 dimensions with 3 numbers, which is not too surprising. If you're into sort of degrees of freedom heuristics for engineering or physics, 3 degrees of freedom in R3 for a point, and so you need 3 real numbers to describe where they are. What is the distance from the origin of this point here? So distance, use Pythagoras. That's definitely not how you spell it. Pythagoras. There you go. The distance from P, X, Y, Z to origin, which is 0, 0, 0, is the following. You have a couple of right triangles here. All right. So one right triangle you have is, it's not what I wanted to do. So there's a triangle here that looks like that, right? So this here is a hypotenuse of a triangle that makes a right angle here. So there's one leg that is given to you by Z. So this is how high up you are. This is Z. And then there's another, this red arm here casts a shadow from the origin to the shadow of the point here, right? Maybe it's better. Sorry, for illustration's sake, let me switch this triangle around. That triangle's the same as this triangle here, right? So you're sort of restricting yourself to this plane here. There's a height here that's given to you by how high up you are, right? This leg of the triangle Z. And then there's an arm here. That's another leg of this right triangle. And together, this leg squared plus this leg squared must be equal to this hypotenuse squared by triangle, by Pythagoras, right? Now, this distance squared is precisely it's the distance of P to the origin squared. So you just got to take the square root of this squared plus this squared, right? Now, this length is L. Let me call this little l. L is equal to, L squared is equal to x squared plus y squared, because on the xy plane here, you could draw a right triangle here confined to the xy plane. And this is a hypotenuse, right, of the right triangle with legs x and y, right? So this is L squared is equal to x squared plus y squared. L squared plus z squared is equal to this distance squared. So this distance is going to be equal to the square root of x squared plus y squared plus z squared. Now, in general, let's say you have, if P has coordinates x0, y0, z0, and Q has coordinates x1, y1, z1. So I could draw, let's say P is some other point here in 3 dimensions with a different set of coordinates. Then you have distance from P to Q. Let me just square this, all right? So I don't have to write the square root sign. It's nicer, but in actuality, when you want the distance, you just take a square root. This is going to be given to you by x1 minus x0 squared plus y1 minus y0 squared plus z1 minus z0 squared. All right, so that's the distance formula. And this also follows from, it's the same picture here, right? Basically what you want to do is you translate everything so that in the reference frame of Q, P is at the origin, right? So what you're doing is you're pretending x0, y0, z0 is right at the origin here, and you're comparing the distance of Q to P, right? So you want to find the distance of x1 relative to x0, y1 minus y0, z1, z0, and the same sort of analysis applies as one previous. Okay, so if we know this is the formula for a distance, does anyone want to venture a guess for the equation of a sphere? So, let me just draw a mini diagram for what the situation here was. This was if you have a point P and you have a point Q, then the formula I wrote here gives you the distance between them, or the distance between them being the straight line path that joins them, right? So this is the distance. So Gabriel has a formula for the sphere. It's x squared plus y squared plus z squared equals r squared, right? So that gets me, right, so the first one gets me a distance, the set of points of constant distance r squared from the origin, right? That's x squared plus y squared plus z squared equals r squared. Now I could also, modify this to be centered at any x naught, y naught, z naught, right? So a sphere of radius r centered at a point P with coordinates x0, well, let's just call it ABC now, is the set of points in R3 of distance, well, maybe I should specify, so this is a constant distance, R, let's make sure R is positive, from the center, from P. All right, so it's a set of points that satisfy distance, let's say, so Q is equal to, let's say, X, Y, Z, is part of the sphere. If distance from P to Q is equal to R, right? So this is the same thing. This is equivalent to distance squared from P to Q must be equal to R squared, which is equivalent to, by our distance formula here, the fact that X minus A squared plus Y minus B squared plus Z minus C squared equals R squared. There's your formula for a sphere of radius r centered at a point ABC. It's given to you by this equation here. Note terminology. A sphere is a two-dimensional surface. A ball is 3 dimensions, is a 3D region contained within a sphere. All right, so just think a ball is a bowling ball, a sphere is like a basketball, for example. All right, so that's what we have, strict equality here. And here you could also write this as e.g. a ball is described as x minus a squared plus y minus b squared plus z minus c squared is less than or equal to r squared. Sometimes, depending on the specifics of the situation, I might want this to be a strict inequality, or sometimes I would also allow it to contain the sphere itself. It just depends. But these are all balls. All right, let's do some practice to familiarize ourselves with what's going on here. So let's say I have a point here. All right, so let P be the point minus 2, 5, and 4. What is the distance from P to the following? All right, to the xy plane, the xz plane, and C, the yz plane. And let me maybe clarify this. If I have a Cartesian coordinate system R3, the xy plane just means take z equals 0 and pretend you're confined to the xy plane. All right, so when z equals 0, you're on the xy plane. When you're on the yz plane, similarly, you're at x equals 0, and just looking at this sheet here spanned by y and z, just here. All right, and similarly, the xz plane is when y is equal to 0, and you're just confined to that sheet here. So I should maybe write this here. Xy plane is at z equals 0. Or sorry, xy plane is z equals 0. Xz plane is y equals 0. And yz plane is x is equal to 0. So for this exercise, maybe, so we have a formula, right, for distance between points. But I would suggest maybe when you're thinking through this, think about what it means for the distance of a point from any of these planes. So we're talking straight line distance, right? You want to find the shortest distance P is from, let's say, the xy plane. So in this case, what's really the only dimension? Let's say I'm measuring P with these coordinates, and I care about how far P is from the xy plane here. In other words, how high off of the ground xy is P? What's the only dimension I really care about here? Right. So if you reframe it like this, then you don't really have to bother with any of these distance formulas, right? In fact, with the tools that we have so far, I haven't actually taught you how to find a point P from any two-dimensional object quite yet. But from the coordinate planes, it should be more intuitive, because what I'm asking here, how far is P from the XY plane? Well, it's how far is P off the ground, and that's just the absolute value of Z, right? Because P could technically be below ground here, and distances are always positive, right? So you want to take the absolute value. So in this case, the interpretation is as how far is P off the ground? Z is equal to 0. And the answer here is you read, well, how high are you, right? You're 4 off, 4 units, right? So this is 4. And now what about the XZ plane? What would that be in this case? So from Z equals 0, your distance is 4, because that's what Z is. So here, this is a Y coordinate, right? So this is indeed, you read off the Y coordinate here, and this is 5. And now what's your distance to X equals 0 in this case? Right, so not exactly X coordinate, but the absolute value, right? So this is going to be X is equal to plus 2, right? Plus 2. So remember this, right? This is, distances are always non-negative. All right, so hopefully this gets you a bit of intuition of what P is, or what distances are to planes, right? At least another example. Let P be as above, and let Q be the point minus 2 to 0, and let's say 100. Okay, which point is closer to the XZ plane, XZ plane? B, which point is closer to the origin? Okay. What's the answer to A? Right. So in fact, where is this point A? It's lying exactly on the XZ plane, right? It's on the XZ plane because there's no Y coordinate here. Your point at 0 Y coordinate, right? Which means Y is 0 and your point is somewhere on the XZ plane here. So your distance is quite literally 0. So Q is the answer, lies in the XZ plane. And now which point is closer to the origin? Well, let's see. Distance from P to the origin squared, right? What's that going to be? Well, that's going to be minus 2 squared. Just realized you can't see what P was. Sorry, guys. Minus 2 squared plus 5 squared plus 4 squared. Now distance Q to the origin squared. What's this going to be? Well, this is going to be minus 2 squared plus 0 squared plus 100 squared. All right. So which point is closer? It looks like it's going to be P, right? Because, well, they both have 4 here, right? So that's the same. Now you're comparing 5 squared plus 4 squared to 100 squared. And so 100 squared wins, right? So this is larger than this. You can take square roots if you want, but I mean, it's the same with just not taking the square root. So you have distance P to O, the origin, is less than distance Q to O. So this means that P is closer. I guess I should have written this in blue. Okay, so P is closer. All right, let's do a slightly different question here, and let's take a look at spheres. All right, so suppose I want to find the distance between 2 spheres. Let's say let S1 be a sphere of radius R1 centered at A1, B1, C1. And let's say I have S2 as well. So let S2 be a sphere centered at R2, or sorry, a radius R2, centered at A2, B2, C2. Now suppose S1 and S2 do not intersect. All right, because clearly if I have, let's say S1 is centered at the origin of, let's say S1 is just a radius. You could have 2 balls, right? That there are 2 spheres that intersect each other, and we don't really want that in this example. So let's say S1 and S2 are far enough apart such that these are surfaces that do not bump into each other, essentially. So they do not intersect. They do not intersect. What is the distance between S1 and S2? So let me draw a schematic here, maybe. Say S1 is here, and let's say, it's like the moon orbiting the Earth or something, right? So here's S2. They don't intersect. They have centers at various points, right? So if it has a center here and some radius, and has a center here, some radius. Maybe I'll give you a couple minutes to think through this. How might we find the distance between S1 and S2, given the information we know? So we know the centers of these points, and we know their radius. Okay, so two people are quick on the draw and have agreed, right, on a rough strategy on how to do this. Let me draw this out for you guys, maybe schematically. So strategy. So here we are with two spheres, right? So what we want is, well, there are a couple measurements we could take already, right? So this is, let me call this center P, and let's say I have a different center Q for the second sphere. So one thing I have for sure is a measurement of how far apart the centers are, right? This is given by the distance of from the center P to the center Q. Now I also have, I could deconstruct this in a few ways. What I really want is this portion here, right? This is what I need, because that gets me the, the distance should be, you can measure distances from two surfaces any way you want, or so you can, put a tape measure between these two surfaces any way you want, but the true distance is achieved when your tape measures the smallest, right? So what I really want is this portion here. And so what I can do is I could take the two radii, right? There's R1 here. Is that what I called it? Right, R1, and then there's also R2 here. So find the distance between P and Q, between the centers of these circles, minus R1 minus R2, right? Because what I have is what I want, which is the distance between the two spheres. And if I add distance between the two spheres plus R1 and plus R2, then I get the total distance. So I just do some basic algebra, and this is what I get, right? Okay. So let's just plug it in, right? So this is going to be equal to, well, distance P and Q. That's going to be equal to the square root of well, what do I call these? A1 and B2s, right? So this is A2 minus A1 squared plus B1 or B2 minus B1 squared plus C2 minus C1 squared, right? And so this gets me the distance between the two spheres, S1 and S2, is going to be equal to the following. It's going to be what I have above here minus the first radius minus the second radius. Now let's take another example. Let's find the curve of intersection now. Find the curve of intersection, let's say formed by a sphere of radius, say radius 3. Actually, let's do radius 9, centered at the point, say 2 minus 1, 1, with the following, let's say with the xy plane, and let's say with the yz plane. So maybe, in these problems, it's nice to have some geometric intuition for what's going on. So what would you expect? What would you expect these curves to look like? Do they intersect on lines? Do they intersect parabola? What's the curve of intersection here, formed by a sphere and a certain plane? So imagine chopping a sphere by a plane. What shape should you get? Right. So you would expect some sort of circle. Okay. So the first thing to do is probably find the equation of this sphere. So does everyone have the equation of the sphere? So remember, we're giving its radius and we're giving its center. So what should the equation in this case be? So what's the x portion of this? It should be x minus something squared, plus y minus something else squared plus z minus something squared equals another thing squared. So what's the x minus part here? Right, so it should be x minus 2 squared plus y minus 1, y plus 1 squared, plus z minus 1 squared, to be equal to 81. What do I do for A? How do I find the intersection with the xy plane? So this should be a curve. So it should be some algebraic expression just dependent on two variables, right? It lives in the xy plane now. So what is the equation for this? So remember, here's x, y, z. I had some curve or some sphere at 2 minus 1, 1. So at 2 minus 1, 1, roughly here or something, and then there's a big sphere here. And I'm asking for the xy intersection of this, right? The intersection xy, maybe. Right, this lives on xy, so it should only depend on xy variables. So I can expand and simplify the sphere equation, then equal the equation at z equals 0. Sure, or I just plug in z equals 0, right? So let's see what happens. The xy plane is at z equals 0. So plug in z equals 0, and what do you get? You get x minus 2 squared plus y plus 1 squared, and z has to be equal to 0, right? What you're doing here is you have one algebraic equation that's, these are the set of points that satisfy this equation form this red sphere here. Now, when I'm saying the curve of intersection, it means not only do you need to satisfy this equation, but you need to satisfy the equation for the xy plane, which is z equals 0. So if you want to satisfy the equation z equals 0, you better make sure that z is equal to 0 here. So this gets you z equals 0, which is minus 1 squared. So this is plus 1, equals 81. So this means that your curve here is x minus 2 squared plus y plus 1 squared is equal to 80. Any questions on how I got this? And what is this in plain English? What is this? This is a circle, and where is its origin, and what's its radius? This is a circle centered at, right? So it's centered at 2 minus 1, and the radius is root 80. Any questions? Okay, so next is the YZ plane. So what do I plug in this case? Everyone in chat, plug in what? So instead of z equals 0, what should I do? Right, so I plug in x equals 0, and this gets me, well, x is 0 now, so it's minus 2 all squared plus y plus 1 squared plus z minus 1 squared equals 81. This means that y plus 1 squared plus z minus 1 squared must be equal to 81 minus 4. Right, so what's this picture here? Well, this picture is on the YZ plane. I'm at x equals 0, so I'm looking at, roughly speaking, yeah, maybe I won't draw this. As you can see, I'm not a very talented artist. Something like this, right? Here, that's your purple curve. So this is a circle with center at YZ is equal to minus 1, 1, and radius root 77. I think we'll stop here for now, and tomorrow's class will continue on and start looking at vectors.